So in the previous class, we started to put together the pieces of the puzzle that remained for graphing polynomials. We were able to identify that we need three key components in order to accurately graph a polynomial. We need to know the y-intercept, we need to know the x-intercepts, and we need to know their multiplicities, because that'll tell us, right, sort of how the graph is behaving near those zeros, right? Does it go straight through? Does it bounce? Right? And then the last piece that we needed, right, to be able to graph these without necessarily going through all the motions of a sign chart would be to know the end behavior. Because if we know where the ends of the graph are positioned, right, we sort of have a starting point to launch ourselves off of. And then from there, we can just sort of use zeros and multiplicities, et cetera, and we don't have to go through the process of generating this sign chart from a formula. All right, and so we figured out that it came down to degree and leading coefficient when it comes to end behavior. And we summarized those results on the next page. So it turned out that if the degree was even, right, the ends of the graph would match. Either both would be pointing up, right, in the case that your leading coefficient was positive, or both would be pointing down in the case that the leading coefficient was negative. If the degree was odd, now your ends are mismatched. And this kind of makes sense. This is about what we would expect, right? If the degree is even, they match. If the degree is odd, they're mismatched, right? And it almost seems it's the reverse of what you would think, right? If the degree is odd and the leading coefficient is positive, you actually start at the bottom and end at the top, right? If the degree is odd and your leading coefficient is negative, you start at the top and end at the bottom. That's maybe sort of the opposite of what we would think. But I find that a helpful strategy for remembering exactly how this works is that anytime your leading coefficient is negative, all right, you will always be ending in the negative zone, all right, whether your degree is even or odd. So anytime your leading coefficient is negative, the right-hand side of the graph is negative. And then from there, you can pretty much get to wherever you need. So now that we've got a sense of the end behavior and where it comes from in the formula, we can start using this in conjunction with all the other information that we have to create some graphs. So that will take us to the next page. All right, so let's take a look at the first example. And I've given you some space to write all of the information that you're going to need to come up with an accurate graph. A lot of these things I'm going to move through rather quickly because we are quite practiced at them at this point, and I don't necessarily feel like we need to go through every single step. I'm going to trust that you can factor. I'm going to trust that you can calculate a y-intercept. So if at any point you have questions about where these numbers came from, you need to get in touch. All right, so for example 1, it's, I think, pretty clear to see that my y-intercept is going to be at -8. So I'm going to say 0, -8. And here's what I like to do. Anytime I get a point on the graph, I like to put it on the graph. It's just less for me to worry about later. So 0, -8, that's a point on the graph. Okay, now the degree, I'm in standard form, so it's very easy to see. Remember, if I'm in standard form, it's just the highest power of x that I see. So the degree is 3, and remember, I don't care so much that this is a 3, so much that it is odd. And so now watch what I start to do here. Every time I get a piece of information, I'm adding that information to my graph. All right, so the degree is odd, so I'm already thinking, right, that my arrows are going to be mismatched. All right, and then my leading coefficient, again, this is very easy to see. We're in standard form, so everything is very straightforward. My leading coefficient is 4. And again, I don't care so much about the 4 as the fact that it's positive. okay? So if I have a positive leading coefficient and an odd degree, right, that means that I'm going to start at the bottom and end at the top. All right, so watch how I do this. I just sort of put my arrows here almost as like points on my graph that I'll have to connect later, right? So remember, odd degree, so we're mismatched. My leading coefficient is positive, so I am not going to end in the negative zone, so to speak. All right, and so now the only work that remains to be done is getting our x-intercepts, which of course we're going to have to do by factoring. And I have 4 terms, so I would factor this by grouping. So I think I'm just going to go ahead and group the first 2 terms together. I'm going to come down here. There's just not enough room at the top. I'll group the first 2 terms together. This will work just as well as anything, I imagine. And then, let's see, common factor is 2x squared. So this leaves me with 2x plus 1. And then I'll factor out a negative 8, which will leave me with 2x plus 1. And so then I undistribute the common factor, which brings me to both 2x squared and minus 8 get multiplied by the quantity 2x plus 1. And then notice this 2x squared minus 8, that has a common factor of 2. So let me undistribute a 2. And that reveals a difference of squares, right? That 2x squared minus 4, that can be factored. So now I have 2 times the quantity x plus 2, x minus 2, and then also the 2x plus 1. So now, from here, our factored form, it's much easier to see our zeros. So this 2, right, 2 will never equal 0. That does not produce any zeros. Moving on to the second factor, that gives me a 0 at x equals negative 2, and its multiplicity is 1. My next factor gives me an x-intercept at positive 2, and that also has multiplicity 1. And then my last factor will yield a 0 at negative 1/2, right? That factor goes to 0 when x is negative 1/2. And that is multiplicity 1 as well. So we just have 3 zeros. We do not need this extra space. All right, so let's see. We need to plot all of our zeros. So we've got negative 2, negative 1/2, and positive 2. And so let's see. The first 0 that I'm going to come up at is negative 2. And all of these have multiplicity 1, so I'm just going to go straight through them, right? Remember, if the multiplicity is 1, we go straight through like a straight line, no funny business. So I'm going to start at my arrow on the bottom, come up, go straight through, go straight through. I won't forget to hit my y-intercept, that's important. And then go straight through my last 0 and sort of connect to my arrow there at the top. Okay, that's good. And remember, we're not going to worry about exactly where this peak is or exactly where that bottom should be, right? We need calculus for that. So as long as your intercepts, end behavior, and, the multiplicities are okay on the graph, we're not going to worry about it. Okay, good. Moving on to example 2. Luckily, example 2 is already factored for us, so that's going to save us a lot of work. All right, but it's not so straightforward calculating the y-intercept, so this one I can't just eyeball, or maybe we can, right? Notice when I plug in 0 here, all this other stuff, right? It really doesn't matter. I mean, I'm going to write it, but because of this right here, everything's just going to go to 0. So the y-intercept is at 0, 0. Let me add that to my graph. All right. Next, my x-intercepts, I'm already in factored form, so that's good news. You could look at it as negative 4/3 does not produce a 0 and move on to looking at x squared, or you could look at them as one big chunk and say, hey, negative 4/3 x squared, that goes to 0 when x equals 0. And then that will be a 0 of multiplicity 2. The next factor gives us a 0 when x equals positive 4, and that's multiplicity 3. And the last factor will go to 0 when x is negative 2, and that is multiplicity 1. And that's it. We don't need this last box. Okay, so this is going to be a little bit more interesting because we have different multiplicities. All right, and now we're in factored form, so we need to be careful when considering degree. We have to remember that all of these factors are multiplied together, but it seems like a pretty straightforward situation. There's no exponents inside the parentheses, so I can pretty much just look at their multiplicities, right? So something that is of multiplicity 2, right, times something of multiplicity 3 times something of multiplicity 1, right? There's this 1 there that is implied. That is going to be a total of degree 6. And notice how that agrees with the multiplicities, right, that we found here for our x-intercepts. All right, and again, leading coefficient, normally we want to be careful, but there's no coefficients inside the parentheses, so what you see is what you get. In this case, the leading coefficient is going to be negative 4/3. So at the end of the day, I have a polynomial that has an even degree, so that tells me that the ends are going to match, and the leading coefficient is negative. So that tells me that they will both point down. So let me start adding some more information to my graph. All right, I now know the ends of my graph both point down, so I'm going to add that in. And let's see, I already have an x-intercept plotted at x equals 0. And then I just need one at negative 2 and positive 4. Okay, so let's go from left to right. The first one that I'm going to hit is x equals negative 2 when I go from left to right. That has multiplicity 1, so I'm just going to go straight through. So let's start at my arrow down here, go straight through. Then, at some point, I have to get back around to hit this, x equals 0. But I notice that the multiplicity is even, so I'm going to bounce at x equals 0. So perhaps something like that. And then last but not least, we'll come back down and hit 0 when x equals 4, but the multiplicity is an odd number, so we need to change concavity, right? Do that thing where the curve sort of flattens out and switches how it, in this case, decreases. All right, and so we just sort of do our best. So let's go up a little bit. All right, come back down to hit our 0, flatten out, and then continue on. And we'll go and sort of reach down toward our other arrow. And that looks pretty darn decent to me. So these first two examples were relatively straightforward in my opinion. On the next page, we'll get to some examples that, you know, some wonky stuff starts happening. It's a little bit less straightforward. Okay, so in example 3, we have function h. We are, again, already in factored form, so I guess that saves us a little bit of work. But now to get the y-intercept, we need to evaluate h at 0. So we'll have 1/8 times 0 plus 4 squared times 0 minus 1 cubed. So that becomes 1/8 times 16 times negative 1, which I believe will work out to be a negative 2. So our y-intercept is at 0, negative 2. So let's add that in. All right, pretty easy to see our x-intercepts. All right, well, 1/8 will not ever be 0 no matter what x is, so we don't count that. Let's look at this first factor. When will this first factor go to 0? Yeah, we're going to want to be careful here, right? So technically, right, x squared plus 4 equals 0. That gives me x squared equals negative 4. So if I square root both sides, remember, always plus or minus, right? Oh, okay, this is imaginary, right? This gives me x equals plus or minus 2i. So we have two imaginary zeros in this case. And so while they are technically zeros, they will not show up on the graph because when we graph on a real number coordinate plane. So yes, these are two separate zeros, right? We have x equals plus 2i, x equals minus 2i, and they are each of multiplicity 2. But for graphing, we're not going to include them. All right, so that just leaves us at this one factor, x equals 1, right? This goes to 0 when x equals 1, and that is of multiplicity 3. So in terms of actual x-intercepts, just the 1. So let's plot it. All right, the degree. Again, we're in factored form, so we're going to be careful. Okay, now there's an exponent in here, so I need to do some thinking. If I have x squared and then I square that, that will really become an x to the 4th. So if I have something x to the 4th times what will ultimately be x cubed, the highest power of x that I see will be an x to the 7th. So that's degree 7, which is odd. And that tells me, again, that the ends of my graph will be mismatched. My leading coefficient, all right, let me just look inside. Okay, there are no coefficients in here, so the leading coefficient, I can be pretty confident that that's just a 1/8. All right, and that's positive. All right, so if my leading coefficient is a positive 1/8, that tells me that I'm going to start at the bottom and end at the top. So I start at the bottom, end at the top. All right, so I need to go through my y-intercept. And again, I mean, this picture might look very different than oh, wait, I'm sorry, this is multiplicity 3. I do not go straight through. I need to change concavity. So you know what? Let me come in here with my eraser. And let's try that again. All right, I'm going to start at the bottom, come on up here, change concavity. Again, your picture might not be gorgeous. Mine certainly isn't. But hey, not bad for distance learning, huh? Okay, good. All right, I recommend that you sort of take a look back at that one and let everything sink in terms of what the real degree is and why there's only one x-intercept, et cetera, et cetera. And once you've done that, we can move on to our last example. Okay, this is like our boss fight. So in example 4, all right, let's start nice and easy. Calculate our y-intercept. Actually, this is very simple in this one, but we'll write it out anyway. If we evaluate k at 0, we have 0 times, well, who cares what the rest of this is because 0 times anything is 0. So that's a y-intercept at 0, 0. And now x-intercepts, right? I see 3 separate factors, right? 1, 2, 3. All right, so starting with the first factor, that goes to 0 when x equals 0. That's just multiplicity 1. All right, looking at the second factor, all right, this is going to go to 0. Well, if it's not so clear, let's go check. 3 minus 2x, when does that equal 0? So that's when x equals 3/2. And that's multiplicity 1. And now we go to our last factor. Okay, so first of all, I am suspicious because this has an exponent, so I feel like maybe this could be factored, right? So let's go down here and check, right? X squared minus x plus 1. All right, so that means that I would need a product of positive 1 and a sum of negative 1. Yeah, that's not going to happen. All right, long story short, you can't factor it. And so remember, if you cannot factor, you need the quadratic formula. So if I want to know when this goes to 0, I need to use my trusted quadratic formula. And so in this case, b is negative 1. So negative b is positive 1, plus or minus b squared, well, negative 1 squared is positive 1, minus 4 times a times c all over 2 times a. Okay, so when we simplify this a little bit, we get 1 plus or minus the square root of negative 3 over 2. So this is a case where we again have imaginary x-intercepts, right? These are two different answers. We have 1 plus I root 3 over 2 and 1 minus I root 3 over 2. And because they came from this factor up here, all right, they are both of multiplicity 4. All right. Now, just because you see a radical does not mean that it's imaginary. Hypothetically, and I'm doing this in red because this is not relevant to this particular problem, if we had gotten x-intercepts at like, whoops, that's a highlighter. If we had gotten x-intercepts at like x equals plus root 5 and minus root 5, those are numbers. Those are not imaginary numbers, right? The square root of 5 should be a little bit more than the square root of 4, right? So a little bit more than 2. And so if that were the case, right, like if here's 2, whoops, maybe you would just plot it here and label it as root 5. All right, so do not let the fact that there's a radical in your answer convince you that your result is imaginary. All right, it just so happened that in these cases, it worked out to be imaginary numbers. All right, so at the end of the day, we just have the two real zeros. Okay, so now for degree, well, we have a multiplicity of 1, right? We have a multiplicity 1 here, and then we have to think, right? Well, I'm taking something that's squared and then raising it to the 4th, right? So again, this contributes a 1, this factor contributes a 1, and this factor contributes an 8. So this is degree 10. So now when we go to look at the leading coefficient, again, we want to be careful. All right, so I'm just going to clear all this out because if we notice the leading terms of each of our factors, there's potentially some things to look out for, right? For example, I'm noticing that this has a negative 2 attached to it. All right, this has nothing attached to it, so nothing to worry about there. But that negative 2 for the leading term of that second factor there, we're going to want to keep our eyes peeled. All right, so we really have a 1 in front, and then we have this negative 2 in here. And so that doesn't have any exponent, right? The exponent's just 1. So it becomes a 1 times a negative 2. So really, our leading coefficient is negative 2. So in this case, the degree is 10, right, which is even. That tells me my ends will match. And the negative 2 is negative. And so that tells me that they will be pointing downward in this particular case. So let's add that in. Both arrows pointing down. I also have an x-intercept at 3/2. And each of them has a multiplicity 1, so I'm just going to go straight through. All right, and then come down and go straight through the other one. And, perhaps the actual graph looks a little prettier than what I have drawn, but this will do. So I recommend you go back through the examples, paying particularly attention to the parts that were not straightforward. For example, calculating the degree or calculating the leading coefficient, right? But also paying particular attention to how we use the degree and the leading coefficient to add in end behavior to make graphing easier. Okay, you'll have some homework problems that'll give you a chance to practice this. Good luck on those, and reach out if you have any questions.